The theory of infinity corpus contains a wide array of physical and ontological claims. Evaluating this material requires navigating an expansive network of theoretical connections. We are stripping away open physical interpretations to isolate the theorem-bearing core. This analysis follows a strict editorial discipline focused on verifiable mathematical results. This core consists only of components that are mathematically exact and independently reproducible. We do not include any results that rely on external physical postulates. Filtering the corpus through these criteria identifies a unified exact core built upon 4 specific theorems. These pillars are generalized golden invariance, exact quartic descendants, the finite recursion lock, and the Vieta crossover. Isolating these proofs prevents the analytical blurring of mathematical identities with speculative physics. It ensures the framework is evaluated on its formal merits. This 4-part architecture serves as the geometric and algebraic foundation for the system. It defines the formal constraints required by any viable theory of infinity model. Theorem A begins within a complete lattice, I, governed by a monotone refinement operator, F. The operator terminates at K infinity, defined as the greatest fixed point of the mapping. In the corpus, this is referred to as the co-inductive seal. We introduce an extensive monotone operator, psi, which satisfies the stability ratchet inequality. This means applying psi after the refinement F is always less than or equal to applying them in reverse. Because K infinity is a fixed point, the ratchet inequality forces the transformed value, psi of K infinity, to remain a postfixed point. Simultaneously, the definition of an extensive operator requires the value to be greater than or equal to the original point. Constrained by these upper and lower bounds, the operator maps the point back to its original position. The value is invariant. This proves the stability of the core. Recursive transformations defined by these operators cannot dislodge the foundational fixed points of the framework. The parent quartic gate is the polynomial p of x equals x to the 4th minus x squared minus 1. It generates the system's coordinates through 4 symmetrical roots. These roots translate directly to the golden ratio, phi, distributed across the real and imaginary axes. This parent equation can be parameterized to create 2 child quartic families. To demonstrate the resulting geometry, we use the parameter c equals 34 over 55. The first descendant, the reflex child, factors into 2 simple quadratic terms. This yields intersections at the real boundaries of plus and minus 1, and imaginary boundaries determined by the parameter c. These intersections at plus and minus 1 create a fixed bounding box for the roots within the complex plane. The second descendant, the reverberation child, is solved using the substitution y equals x squared, reducing the quartic to a standard quadratic equation. Solving for y results in 2 branches. Because c is positive, one branch is positive and the other is negative. When we resolve back to x, the positive branch yields real roots, while the negative branch yields purely imaginary roots. These polynomials enforce an exact dimensional splitting. The resulting coordinates are algebraic certainties rather than approximations. Theorem C addresses the gate lock family, logarithmic equations defining scale. In many dynamic systems, scaling behavior is described using limits as a variable approaches infinity. The TOI framework instead uses a sequence descending through finite depths, from 8 to 4 to 2 to 1. If a value x sub m is a valid root at one depth, we find the root for the next depth by simply squaring it. Substituting this squared value into the equation for depth m-1 causes the exponent to drop down as a multiplier. This cancels the coefficient and returns the equation to its previous state. Every root at a higher depth mathematically necessitates the existence of its corresponding root at the next level. This demonstrates that dimensional descent in this framework follows an exact finite recursion law rather than an asymptotic limit. The final pillar of the core involves the reciprocal quadratic family and the search for invariant values within the Fibonacci sequence. These quadratic equations are parameterized using sequences of adjacent Fibonacci numbers, such as f sub n and f sub n plus 1. The discriminant of these equations, k sub n, is expanded using Cassini's identity. This allows the terms to be rearranged into a Lucas residual identity, which links the Fibonacci and Lucas sequences. We can use this identity to test the boundary swap theorem. A boundary swap occurs when we take two reciprocal quadratics and invert their outer coefficients, a and c. Using the Fibonacci values 13, 21, 34, and 55, we can construct two swapped equations. On the left, 55 and 21 are the outer coefficients. On the right, they are 13 and 34. We evaluate these equations using Vieta's formulas, which describe the relationship between a polynomial's coefficients and its roots. Vieta's trace for these monic quadratics is the product of the parameters b and c. In both cases, regardless of the swap, we are multiplying 34 by 21. Both equations resolve to a linear term of 714x. This shared linear term means that both pairs of roots sum to exactly negative 714. The 714 crossover is a direct consequence of this symmetry. Because the root sum is determined by the product of b and c, the value remains constant as long as those Fibonacci parameters are preserved. We have now verified the four pillars of the core: golden invariance, Cordic gates, the recursion lock, and the 714 crossover. This core represents the limit of what the current corpus treats as an unassailable theorem. The literature also contains other rigorous results, including Lambert transport identities and the Fibonacci ellipse ladder. These are classified as exact continuations. While mathematically sound, they are not strictly required to prove the central core of the theory. Finally, we address the physically interpretive claims, such as the holographic compatibility theorem. These model-level extensions identify mathematical residuals that resemble the structure of the standard model. This demonstrates internal formalization within the TOI canon, but its relationship to physical reality remains an open question. Conflating these model-level explorations with algebraic proofs is an epistemological error. The framework's strength lies in the distinction between speculation and proof. It provides a stable mathematical bedrock while leaving the broader physical interpretation for future inquiry.